Hi everyone. The next topic is step functions. So last time we discussed polynomial regressions to represent more complicated relationship than straight line relationship between x and y. So alternatively, we can use step functions instead of polynomials. So you can see that piecewise constant function to fit some data. So mathematical formulation is, at first we prepare step functions here. So these are indicator function for some interval. Then after preparing these step functions, we fit y on each components. So here, once you define these step functions c0 to ck, it's not difficult to estimate beta naught, beta 1 up to beta k, because this is entirely linear model with respect to beta naught to beta k. But one difficulty is how to determine these knot points c1 to ck. So these numbers c1 to ck cannot be determined easily by least square methods. So least square is quadratic function of beta naught to beta k, but more complicated function of c1 to ck. So this is illustrative example of step function regression. So this is the same data as the last time. So we have seen that the wage is higher between age 35 to 60. So that idea is well explained by this step function. So younger people have lower wage on average, also older people. But in the middle, because of this cluster, average wage is higher. So same thing apply for logistic version of the regression. So remember that this is the probability of wage is more than 250. So this probability is significantly higher at age between 35 and 65. So in this way, step function can be used to represent more complicated relationship. This is pretty flexible approach. A generalization of step functions is basis functions. Generally, we think about basis functions b1x to bkx. These are any functions such as polynomial or step function or sine curves, cosine curves, or even Gaussian PDFs. Once you determined basis functions, then you can fit usual linear regression to determine coefficients beta naught to beta k. Sometimes it is convenient to avoid multi-collinearity. So we can take orthogonal basis beta 1 to beta k. For example, think about the case that x is between 0 and 1. It is fine to include intercept x squared, but you can see if we include many terms, x to the 9th power and x to the 10th power are very close on this dataset. So in this case, rather than using just polynomials, we can use orthogonal basis. So example of orthogonal basis is two sine functions. If one basis b1 of x is some sine curve, and b2 of x is the sine curve with higher frequency, then b1 and b2 are totally different function, and in fact, in this case, orthogonal basis. So this basis function approach is more convenient to avoid multi-collinearity compared to polynomial regression. Okay, so now you can go to quiz 3.24.1 part 2. Okay, see you then.